Hello everyone, we will continue with another example about the induction motor. According to our given specifications, we have 3-phase, 25 kilowatt output rated power, 460 volt terminal face-to-face voltage, 60 Hz, 4-pole, Y-connected induction motor. And in addition to that, R1, R2, X1, X2, and xm values are given, and we will use the approximate equivalent circuit without RC because we don't have any information about the RC value of this system. So according to given values, first of all, let's clarify our circuit. We have 0.42 ohms R1, we have 0.82 ohms X1, and same value, which means design A type induction motor we have. For XM, the value is 22 ohms. For R2 over S, R2 value is 0.23. But for sleep, let's calculate first of all the value of sleep because it's not clearly defined. In addition to that, our input voltage to the system we phase, and it must be 460 volts divided by square root 3 because of the Y connection, and the current flowing through the circuit, the input current is equal to I1, and for the remaining part of the circuit we have I2. Okay, the last parameter for the circuit before the current calculation should be the R2 over S determination. So let's start with the NS. NS, the synchronous speed, can be calculated with 120 F over P, the pole number. 120, 60 over 4 will be 1800 RPM. And also we know the Nm, the motor speed, and we can calculate the sleep with the expression of Ns minus Nm over Ns. And it will be 1800 minus 1750 divided by the again synchronous speed. So it will be 0.028, or in other words 2.8%. So let's use the sleep in the calculation of R2 over S. So 0.028 will be 8.2 ohms. So for the equivalent circuit, we have the each parameter and we can calculate the equivalent impedance. When we examine the circuit, what we have first of all series connected components, the right side. So let's call it as Z1. For the Z1, we have R1, X1, X2, and R2 over S series connection. Then we have a parallel connection with that group with XM, and it will be the equivalent impedance. So the first one, Z1, will be R1, X1, X2, and R2 over S. According to given values, 0.42, and for the reactance 0.82, 8.2 ohms will be the R2 over S, and for the second reactance we have 0.82 again. So from here we can calculate its value as 8.77 with 10.77 degrees. Now the equivalent impedance can be calculated with the parallel connection of Z1 and XM, 1 over XM, and its parallel connection with Z1. From here, if we use the given and calculated values, the magnitude of the equivalent impedance will be 7.7 and the angle will be 31 degrees. Now the input current of I1 can be calculated. How? By using the voltage and the calculated impedance. I1 will be equal to per phase voltage divided by equivalent impedance. So the rated terminal voltage, which represents the phase-to-phase voltage, is given as 460 volt. We will divide the square root 3 because of the V1 per phase voltage. And according to our calculations, equivalent impedance is equal to 7.7 with 31 degrees. And 34.49 with minus 31 degree will be the I1. Input current will be 3 times V1, I1 and cosine theta. According to our system parameters, V1 460 over square root 3, the I1 according to our calculation for 34.49, and the cosine theta will be cosine 31, the angle of current according to reference voltage. So 23.6 kilowatts will be the input power for this machine. Now let's continue with the air gap power. For air gap power, it is the total power which is transferred to the rotor part. We can use 3 times the current for the secondary side, for the rotor side, times the total resistance on the rotor part. So to be able to use this expression, we need to calculate the I2. What was the I2? The secondary side current which is flowing through the R1, X1, X2 and R2 over S for this circuit. And we can make a similar calculation with I1, and we know the voltage between these nodes, and we know the total impedance of this part, which is Z1, and we can calculate the I2. So before the air gap power calculation, I2 must be calculated with V1 divided by Z1. So 460 over square root 3. And the Z1 8.77 with 10.77 degree. So 30.3 with minus 10.77 degree ampere will be the secondary side current. Now we can calculate the air gap power. Air gap power will be for 3 phases 30.3, which is the current of I2 secondary side, rotor side, times 8.2, which is the R2 over S. So 22,585 watts will be the air gap power. What else? We can continue through the rotor part, and the rotor copper losses can be calculated. Again, we will use 3, the current flowing through that part square, and for the rotor copper losses, the representative parameter is R2. So 3 times 30.3 square times the R2 value, which is 0.23. That means 633.5 watts will be absorbed by R2. Then we can continue with the output power calculation according to our parameters. We can start with the air gap power value. Then we need to subtract the rotor copper losses and the mechanical losses, which is the rotational losses, which includes friction, windage, and the stray losses. So 22,585, which shows the air gap power, minus 633.5, which is the rotor copper losses, minus 60 watts, which is the rotational losses, which is given in the beginning of the example. So from here, the output power can be calculated as 21,892 watts. And the efficiency finally can be calculated with the ratio of output over input as a percentage. So 21,892 divided by input power, which is 23,600 watts, it will be 92.7%. Thank you for watching.